So now we would like to design a circuit where one input and multiple outputs. Input value would be forwarded to the selected output line based on the control. How can we design this particular circuit? So let's read it again. We have one input and multiple outputs. Now the input value, whatever is the input value, 0 or 1, that would be copied or that would be forwarded or that would be connected to the selected output. So there could be n number of outputs and it has to be connected to only one of the output depending on some of the control bits. It looks like it's an inverse circuit of multiplexer. In multiplexer, we had multiple inputs, one output, and this one output was selected based on the control lines. Here it is reverse. We have multiple of these outputs but only one input, and control is selecting that input should go where. So because it is sort of reverse of multiplexer, it's called, this particular thing is called demultiplexer. In short, we also call it demux. So if 1:8 demux need to be created, then this particular input is x, and I would require 3 control lines. How many control lines would be required? So let's say the number of outputs are n, then the number of control lines has to be log of n, or actually ceiling of log of n base 2. So if there are 4 outputs, then number of control input would be 2. If number of outputs are 8 here, then the control inputs would be 3. Similarly, for more than 8, let's say 10, then number of control signals has to be 4. So if ABC is 0, then this Y has to be copied to this particular first output. So similarly, second output, third output, it all depends on what is the value of ABC. I can also keep it like this, that the Y0 would, if I need to implement this as a Boolean logic, then I will say that Y0 is essentially x dot a dash dot b dash dot c dash. So essentially when ABC is 0 0 0, then whatever is the x that has to be passed to Y0. Now because ABC is 0 0 0, so this particular control signal will become 1. So whatever is the value of x, if it is 0, Y0 would be 0. If x is 1, then Y0 will also be 1. Similarly, Y1, Y2, Y3, Y4. So you can see these are all mean terms. So the mean term 0, mean term 1, mean term 2, mean term 3, 4, 5, 6, 7, and all of them are ended with x. So in this way, we can say the cost of my demultiplexer is actually equal to, if the number of outputs are n, then the cost is equal to n AND gates. Okay. And how many inputs to each AND gate? It depends on number of control lines and input. So the total number of gates would be total number of control line plus 1, that many number of inputs to each of these AND gates. So this is the cost of my demultiplexer. Similar to multiplexer, this is one line multiplexer, so that means it is 1 to 8 demultiplexer, but the input size is single bit. There is a good possibility that I can have a similar to multiplexer. There could be a multiple, so all these inputs and outputs could be buses. So that means there could be multiple bits present here. So again remember, so when we are saying multiple bits are present, they essentially means in terms of implementation, this is multiple copies of this 1 to 8 demultiplexer. It's a simple copy of all of them. Let's say this x is 4-bit input. So in one of these demux, x0 is given as an input, in other one x1 is given as input, the other one x2 and x3 is given as input. So whenever we say a vectored or bus based demultiplexer, in circuit it would be implemented as a replicated copies with different inputs. One of the each bit would be given as a different one input to one of these demuxes. Okay, so this is how these demultiplexers can be designed and can be utilized. Now if I have such a standard circuit, I can call, so from now onwards whenever we are designing we can think of using this particular circuit if required, but where it will get utilized. Usually wherever your multiplexer is used, demultiplexer will also be used on a similar places. So where it is used, so for example your multiplexer is used in routers to connect one of the input to multiple outputs. Now when the packet which is going forward, it will use multiplexer. Whenever packet is coming back, then it has to use demultiplexer. So this way these demultiplexers are used in complementary to the multiplexer. Okay, or wherever we see that this one output has to be forwarded to multiple of the selected inputs, so we have to see that in which scenario this will fit in. Similar to this demultiplexer, there is also another popular circuit, a commonly used circuit, which we call decoder. So in this decoder, the difference between decoder and demultiplexer in a way is that if this particular line x is 1, if this x is 1, then based on the value of a, b, c, one of the output is going to be 1. So in other words, let's say if a, b, c, the input is 0, 0, 0, then y0 would be 1. If the input is 0, 0, 1, then y1 would be 1. So in other words, this decoder will have only one of the output as 1, all others as 0, and it depends on what is the input pattern. Now there could be n output and the number of input would be log n base 2. Okay, so if there are 8 outputs, there would be 3 inputs, and based on the 3 input, one of the lines would be selected. One of the line would be high, all others would be 0. So this is also quite a popular circuit, and you can say it's a very similar to demultiplexer. Okay, but the cost is less. Now cost of decoder, I can clearly say that it will have n AND gates. Each AND gate would have number of inputs equal to the number of control inputs. Okay, so this is called 3 to 8 line decoder, and you can see the other purpose, you say you're decoding. So because now you have n numbers, you wanted to select which particular number it is. You have n LEDs, let's say, which LED to lit, then only let's say there are 16 LEDs, then only 4 bits are sufficient to know that which LED should lit. Okay, so this way this decoder can help us in identifying which number it is. Each number is represented as a different wire. Now to see the utilization and how these encoders, how these decoders, multiplexers, demultiplexers could be utilized, let us take one design example. So with this design example, let's try to understand which one to be used, how to be used. So in this design exercise, let's try to understand what this question is. So we are assuming that we have a special kind of a hardware. The hardware can store 1 bit of data, and let's call this hardware as a memory cell. Now you can see this memory cell could be an electronic circuit, could not be an electronic circuit. It is saving 1 bit of data. You see whatever you call memory. So some of these memories, they store data in form of magnetic polarity. Some optical discs store it in terms of light, whether there is a cavity or there is no cavity. And if we are storing this value as a charge, if there is no charge then 0, if there is a charge then it is 1, then we can call it a memory cell. So let's not go into the implementation internal of this memory cell, but we say that there is a hardware which can store 1 bit of data. How to read it? So this particular memory cell will have one output R. So this R, if we see, it always reflect whatever is whatever inside value is there. If inside value is 1, then R will always be 1. If inside storage is 0, then R would be 0. Okay, and there as an input, so we should be able to write this memory cell. And let's say we have these two inputs which help us in writing. If E is 0, so if E is 1, whatever is the content of W, that will get written to memory cell. But if E is 0, then nothing happens. So that means whatever is the content of W will be written into this memory cell only and only if E is 1. Otherwise, W does not will not be written to this memory cell. So essentially, it's a control. E is a control signal or enable signal, which says that whether this memory cell has to be written or should not be written. So this way we should be able to control what to be written to these memory cells, what not to be written. So this is the basic entity we are assuming that this is given as an input. Now the design exercise is we want to design a memory which has 16 such memory cells. Now because there are 16 cells, we can access them using 4 bits. Let's say the bit address is 000, then I can access cell number 0. Similarly, bit address 001, then 0001, then I can access cell number 1. So along with this address, we also have if W is 1, then data in would be written to that particular memory cell to which this address is mentioning. And otherwise, this address will always give out whatever is written in that particular address, in that particular memory cell. So in other words, if my W is 1, then data in will go to that particular address. If W is 0, then whatever address is given, that data out will read out from that particular memory cell to whatever this address is pointing to. Now I want to design such a circuit which will do this functionality. Okay, so whenever we are designing a circuit, it's always better that first we clearly draw such kind of a diagram which clearly segregate what is input, what is output. Here we know that data in is 1 bit input, data out is 1 bit output, and address is a 4 bit input, W is also 1 bit input, and inside this there are 16 memory cells which has a description like this, that which has two inputs. Each cell has 2 inputs, W and E, and 1 output R. Now how to design this? So for designing, the first step is we have to see what would be the input and output, what is going to be their parameters, like what are the sizes of input output. The second is to describe the functionality clearly. So here we see there are 2 functions this particular circuit is performing. One function is read, so that means data out will read given an address. So given an address, it will go to a particular memory cell, and whatever is the value there, it will read out, it will go into data out. It should be connected to data out. While the other functionality is write, so that means data in should be written to a memory cell. Which particular memory cell? Whichever is the given by address. And data in would be written if W is 1. Now, given this functionality, let us think out that if I need to design, how should I go about it? Since we have studied this multiplexer, demultiplexer, decoder, then mind is forcing us to think that possibly we have to use any of them. Maybe we were supposed to use tri-state buffers also. So now let's first consider write. So in case of write, what do I want? I have one input data in, and that particular input data in I have one particular input data in, and that particular input has to go to any of the one of the 16 memory cells based on address. So it looks like that it's good to use the first thought is coming that I should use demultiplexer. Now in case of demultiplexer, what would happen that my data in would be given as an input, and my control would effectively be the address. It's a 4-bit address, and whatever are the output, 16 output of my demultiplexer, so all of them I should be connecting to W0, W1, W15 up to W15. What does it mean? It means that if my address is, let's say, 0000, yes, and then whatever is data in, that should go to W0. So if data in is 0, then W0 will become 0, and data in is 1, W0 will become 1. What would happen to all others? W1, W2, W15, all of them will also be 0 if the address is not selecting that particular W. So, or that particular memory cell. So if that particular memory cell is not selected, then those inputs would be 0, and data in will go to W0 or a particular cell if that particular address is 1. So there are two issues here. One, that we still have to generate E signal or enable signal of each memory cell. Okay. The second is that because of this demultiplexer, using of demultiplexer, all of these W values are either 0 or 1. It depends on the address. Okay. So it looks like a duplicate effort. So because I also have to first of all generate my enable signal, the second thing that whatever is my data in is going to a particular W, it become sort of unnecessary. So rather than that, what if I do? So then we have to discard this, and what we have to do is, if we focus on generating enable signal rather than W signal. So what we will do is we will connect this W of the final interface, memory interface, 16 cell memory interface. The W, we remember, is, if it is 1, then it would be written. If it is 0, it won't be written. Now this W would be used to generate the enable signals, and address is used to do a demultiplexing. So address is working as a control, and W of the input is going to generate the enable signal, and data in is given to connected to all W0 to W15 of our memory cells. So this way, what we are able to do, that this control signal or enable signal is generated using the write, using this 1 to 16 demultiplexer. Now let's think that can we use decoder here. Decoder, perhaps it can be used if we use this address. If we use address as an input to decoder, then there would be 16 output, of course, and now those 16 output has to be ended with the write, so that if write is 1, then only that particular unable signal will be 1, otherwise it has to be 0. So that's how we have to think rationally. We have to see that which particular circuit can be used so that my end requirement can be met. Now similarly, this unable signal would be generated using a demultiplexer where input is W and data in is connected to all W0 to W15 signals. What about read functionality? Read, we can see that in read what we are doing, that data D output from memory cell is always available, so we simply have to read based on the address specified and we can always read it. So simply we can have 16 to 1 mux where address can work as a control and D0 to D15 could be connected to input of my multiplexer, and then I can say my output is data out. Here the specification was more or less clear. There was less confusion because it was clear that I have to get the output from one of those memory cells. So there are 16 inputs and out of that I have to select one. So I can use multiplexer here. Overall, the complete design would look something like this, that there has to be 16 memory cells. Overall design would be, there would be 16 memory cells, let's say starting from M0, M1 to M15. Now first of all the data in signals, like there would be if we remember that my memory cell has 3 inputs, W, enable and D. So all the W signals would be connected to data in. Now the question is, if I am writing data into all the W signals, then to whom this particular data signal would be read, would be written. Now this W would be written to only that particular cell where enable is 1. Okay, so enable would be 1, so there would be enable signal. These enable signals are essentially coming from my demultiplexer. So this demultiplexer address is given and the write of the input is given, the control signal is given as a demultiplexer. So all the enables would be determining that which particular write will be, which particular data in would be written to memory cell. Now D here, all of them are connected to my multiplexer, and then address is determining that which particular one would be given as a data out. Let us say there is a further condition that I have to read only if my control signal is 0. In that case, I can have this multiplexer which would have either enable signal as an input. So but we can always discard. We can say that this data out we are not going to read, so we can have another AND gate here that this data out would be read only if my read signal is 0. Okay, so this is how, like, whenever a design question is given, we have to think over it. We can break it into smaller functionality and we can work on all those functionality independently to come up with a complete design. So the summary of this lecture is that we have learned about how the signals are connected, what could be the solution if we have to connect multiple of the outputs to the same input. So that was suggested as a tri-state buffer. And then we have seen that how demultiplexers can be utilized or how decoder can be utilized. Okay, so one more thing which we have learned, that in our digital circuits, our final output should be either 0 or 1. If it is X, then it is undesirable. If it is Z or high impedance, then also it is undesirable. So we have to design a circuit aiming that all my outputs, all my intermediate signals should be clearly 0 or 1. we have to avoid the value of unknown or high impedance as much as possible. Thank you very much.